This video is the last on the binomial distribution, and it's on a topic called normal approximation to the binomial distribution. If you think about those words, it's helpful. What we're trying to do here is actually use a normal curve to approximate a binomial distribution. And under the right conditions, that works better than it does under conditions that aren't quite right. So one of the things you need to know is when is it okay to use a normal curve to approximate binomial distributions or binomial probability. Now, hopefully you've watched the videos. We ended the last one by making a binomial probability distribution showing the probabilities of 0 to 10 defective switches out of a sample of 10. And the distribution looked like what you see here. There's nothing normal looking about that. So what you need to understand is what are the conditions that actually make a distribution look normal. So I'm going to attempt to do that here. Here's a little applet. This is actually the same distribution. You'll notice the sample size here is 10. The probability of success is 0.1. Those bar heights correspond exactly to what I drew here. It looks a little nicer because they use software. And again, it doesn't look the least bit normal, even though there's an attempt to draw a normal curve over it. But watch what happens if I change the sample size here. So I'm going to increase the sample size slowly. I get it up to 30. Well, it's looking more normal, but it's still skewed to the right. What if I get it up to 50? Well, that's starting to look more normal. What if I get it up to 60? Well, that's getting more normal still. And if I change the probability to 0.2, for example, I get something that's remarkably normal looking. Let me run this back down to 50. So here I have a sample size of 50 and a probability of 0.2. And that looks pretty normal. It looks like drawing a normal curve over the binomial probability distribution is a decent approximation of that binomial probability distribution. As p gets smaller, it gets less normal, more skewed to the right. As n gets smaller, it gets less normal, more skewed to the right. But if I make n and p in combination big enough, it starts to look more normal. And if I make p 0.5, it looks quite normal. So the key is that n and p in combination have to meet certain conditions. So if I want to draw a normal curve and use it to approximate binomial probabilities, then I have to meet these conditions. So let's say this, normal approximation. Suppose that a count x has a binomial distribution, like the number of defective switches, with n trials and a probability of success of p. When n is large, the distribution of x is approximately normal, much like I just showed you with that applet. And it's approximately normal with this mean, n times p, and this standard deviation, the square root of npq from the last video. Well, you should be asking yourself, how large does n have to be before a normal curve becomes a good approximation? And there's a rule of thumb. N times p has to be greater than or equal to 10, and n times q has to be greater than or equal to 10. And so if you look again at that applet, the last thing I left you with, that n of 50 and p of 0.5, n times p is 25, that's plenty big enough. But even when I run p down to 0.2, n times p is 10 or more, it still looks remarkably normal. So under those conditions, we're okay using a normal curve to approximate the binomial distribution. So as the number of trials for the binomial distribution gets larger, it gets closer and closer to a normal distribution. Well, why would we do that? I mean, we can calculate things with a binomial formula quite accurately, but the world loves normal distributions. So if a normal distribution does things as well or reasonably as well as a binomial distribution, it's nice to be able to use a normal distribution. We're going to work through a couple quick examples here. So pause me, read this. Okay, so we're doing a local poll here. Consider a poll of 400 adults in Richmond that asks the question, do you approve of President Obama's plan to remove troops from Iraq? Okay, it's an older question. Suppose we know that President Obama's approval rating on this issue nationally is 92%. But what's the random variable here? Okay, we're taking a survey. What's random? Think about the question we're asking. The random variable x is number of what? Pause me. Right, it's the number of people out of 400 who approve, if I can write, who approve of its plan to remove troops from Iraq. Is it binomial? Well, let's think through it. You have to do this in context, right? Are there a fixed number of trials? Yes, we're talking to 400 adults. What's the probability of finding an adult who agrees with the statement? Well, we're presuming we know 92% of adults agree. So if we pick an adult at random, as far as we know, there's a 0.92% or 0.92 probability that person will agree. It's 400 people from the city of Richmond. We can assume that all those people are independent of each other. And we have, what am I forgetting here? We have a fixed number of observations for, and everything's a success or a failure. Either they approve or they disapprove. There's only two possible outcomes. So yes, it's binomial. It says calculate the binomial probability that at most 358 of the adults in Richmond answer yes. Pause me, calculate that binomial probability. All right, so we're doing full work here. We've already defined our random variable. N here is 400 adults. P, the probability of success, is 0.92. And in this case, we're interested in 358 at most. We'll write a probability statement. At most, 358 is less than or equal to 358. So because it's an inequality, you should have done binomial CDF, 400 trials, 0.92 chance of success. 358 successes or fewer. And if you did that math correctly, you would have gotten 0.0441. So that's the binomial probability of taking a poll of 400 and finding 358 or less who approve of Obama's plan, if in fact 92% agree with the plan. Right? So the probability of getting 358 or less, if in fact 92% of the population agrees with the plan, is about 4.4%. Right, question C here, find the expected number of people. Find the standard deviation for the number of people who would agree. Pause me, calculate those. Well, expected number, this is a binomial probability question. The expected number is equal to n times p, which is a way of saying if I survey 400 and I knew 92% would approve, then the expected number of people who would approve would be 92% of 400, which is 368. Now, the standard deviation is an interesting idea. The standard deviation formula was the square root of n, p, q, or 1 minus p, which is the square root of 400 times 0.92 times 0.08, which is 5.42. Well, what does that mean? That means if I took this poll over and over again, I wouldn't get 368. I'd get different answers every time I did. I wouldn't necessarily get 368. I wouldn't necessarily get the same number of people who approve. There'd be variability in the number of people who approve. So that's a measure of the variability I could expect over any survey. D says, perform a not normal approximation to answer the question in B. And compare the results of the binomial and normal approximation. Is the normal approximation satisfactory? Well, you're asked to perform a normal approximation to the binomial probability. Well, the first thing you should ask yourself is, am I even allowed to do that? There's a condition. And these conditions such as these are going to start showing up in some of the math we do. The math's allowed under certain conditions. Well, we said n times p and n times q had to be greater than or equal to 10. Well, let's see here, I keep adding blank pages. Sorry, here we go. Right, so we're going to do, are we allowed to do normal approximation? We have to check the conditions. Because n and p in combination have to be big enough. Well, n is 400, p is 0.92, certainly 400 times 0.92 is greater than or equal to 10, but check both. 400 times q, or 1 minus p, 0.08, that's greater than or equal to 10. So we've checked the conditions. Yes, it's okay to use normal approximation. All right, normal approximation, that's normal curve math. We've done this a lot. I'm interested in the probability that 358 or fewer will approve of his plan. Well, normal approximation, what's my mean? Well, we just calculated that. It's 368. What's my standard deviation? We just calculated that. It's 5.42. And I'm interested in the probability of getting 358 or fewer. Right? Your work includes a normal curve showing mean and standard deviation. We've got a probability statement. Now I can use calculator speak if I'd like. From something very small, you could use 0 in this case because it's practical, or if you just like being consistent, you could use -999. To 358, where the mean is 368, and the standard deviation is 5.42. And if you do that math, you would get 0.0329. Well, hold on. Here I got 0.0329 when I did the probability. Back here I got 0.441. Why are they different? Well, the clue is this. It's an approximation. And the bigger the sample size, the better the approximation will be. The bigger n times p is, the better the approximation will be. So that's normal approximation to a binomial distribution. You need to calculate the mean. That's where this formula comes in. You need to calculate the standard deviation. That's where the standard deviation formula comes in. And you must check the conditions before you do the math.